Okay, good morning. So yesterday, I think you heard about neural networks from Swamin Maiti, and today I'm going to talk about a couple of neural network architectures that are most commonly used, and one of those is convolutional neural networks, and then autoencoders. And after this lecture, I want to show you a bunch of examples using neural networks or machine learning. Okay, so why are you interested, or why are we interested in neural networks per se? Okay, so what we saw is that given we can actually build a linear model m0 plus m1x, or you can have m0 plus m1x plus m2x squared, things like that. So polynomial, so it's all linear models, right? Now if you have a vector y and a vector x, that means your input and output, it is a linear model in m0s, in m, but it's non-linear in x. Okay, and now we are interested in solving for m, right? And that is why this is a linear problem. Okay, and so your nonlinear problem would be something that I think I showed you yesterday, where you can say that my y is equal to m0 times sine of m1 times 2 pi plus m0 cube. So that would be a nonlinear function, right? Now, so you can now think about this problem where we have an input that is of large dimensions, or it's not, the dimension is more than one, and your input is more than one dimension, and y is also n-dimensional. Okay, so how do you relate these two? The linear model is you can use something like a polynomial, and you can say that here I can have something like m0 x0 m1 x1. It's a hyperplane, right? But beyond that, it's difficult to do. And also that there can be a large number of nonlinear functions that we don't know. So to address that, neural networks were invented that can build arbitrary nonlinear functions between the input and the output. Okay? So the way it works is that I have a set of input neurons, right? This is my input layer. Then I have what we call a hidden layer, and then I have output layers, right? So in a dense network, each neuron is connected to every other neuron, right? So, and the way it works is that this one also goes here, 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 and here, right? So what you do here, for example, you have some weights, W, one is, say, the input, and this is your output. W11 x naught plus W12 x1, and so on. And plus there is a bias term, you can call that W0, and then you sum. Okay, so you're getting a linear combination of all of these input neurons. So this is my x0, this is my x1, this is my x2, and so on. Then after that, we run it through an activation function, right? And then activation function can be can have different forms. I think someone already talked about that. But I just wanted to refresh your memory, and that will help you to switch on or move on to the next thing. Okay, so this creates a nonlinear function, and the type of nonlinear function that you get depends on what's your activation function, okay? But then you are restricted, right? So the idea here is to put a bunch of these layers with different number of neurons, and then what you have, let's say that I have input, then I have hidden layer 1, hidden layer 2, hidden layer 3, and then I have the output, okay? So that's my input. This is my hidden, the best thing is to say that these are different hidden layers, 1, 2, and 3, and that's my output, right? And you saw that these are propagating forward, right? Take the input, multiply with the weight sum, and then run through this. So what is the output? The output is basically nothing but you have, let's say that I call this F1, okay? That gives you this output. Let's call this F1, okay? But then this F1 is then acted upon by F2. Then we have F3 and so on, right? So this is a cascaded application of a whole bunch of nonlinear functions. And by doing that, we hope that we are able to establish a nonlinear relationship between input and output, okay? So this may appear, well, this will definitely raise a question like, how do we know that we can basically generate any nonlinear function, right? It turns out that there is a theorem. It's called universal representation theorem. And that tells you that given enough complexity in the neural network, you should be able to build any functions. Not only that, it says that if you have even one layer with sufficient number of neurons, then you can actually build any nonlinear functions. So that is assuring, but there is a caveat to it. You have this tendency of adding more and more layers, more and more neurons, right? And what can that do? It can give you a function that will fit your data perfectly, right? But remember the very basic linear regression problem that we did in the class. I said that the model complexity increase gives you lower data misfit, but that may not always be a wise thing to do because you might be overfitting. So here also you have to be careful when you design a neural network. You have to be careful that you are not overfitting your data, okay? So that's number one. Number two is that as you add more and more layers, you're doing more and more calculations, right? So here you can see that for each neuron, it is doing so many multiply and add, right? And this is basically repeated for every neuron, right? And so this is computationally quite expensive, but the sum, yes?
Said all the neurons in the input are connected to the hidden neurons, all the neurons of the input. So suppose we have more than one hidden neurons, then all the hidden neurons are connected to the next hidden neurons of the neurons.
Yeah. That is the original idea of neural network, and this is and that is called dense connection, okay? Densely connected neural network. So you can find out just looking at this equation how many multiply and add you are doing, right? And that is basically that is what gives you floating point operations. And you are so each for each neuron you are doing certain number of multiply and add depending on what is the number of output neurons. Okay. So the original neural network model was essentially input and then you have an output. Then people added one hidden layer. And now we are using a lot of layers, okay? But there are ways of putting those in there without actually overfitting, but that's something we'll talk about later. But when you have more than two layers, two hidden layers, that is generally called a deep neural network, okay? So there is nothing sort of fancy about this term. It only means that you have many layers, okay? Okay, so today what I'm going to talk about is a new architecture. It's called convolutional neural network. As the name implies, it depends on it basically this convolution operator that is involved here. So why convolution operator and how it is used? Okay, so the idea of CNN was actually used in analyzing images, okay, to start with. So convolutional neural networks were inspired by early findings in the study of biological vision, okay? So you need to think about how we view an object, right? Say, for example, if I'm viewing this camera with a tripod, and I try to remember it, I don't remember all the details, right? So there are certain features here that is captured first. And then based on those features, I build the image in my brain, right? So this is the idea of, this is the basic idea of biological vision. So what they say is that in the biological vision, what you do is when you view an object, then you basically look at certain features. Say, for example, you look at some dark and light bars, okay, with certain orientations. And this would be called simple cells. So simple cells actually keep track of the light and the dark bars. And then complex cells actually combine those informations to finally build the whole image. This is what is done in our brain. That is what the computer, that is what biological vision people have discovered. So how is that implemented in a computational algorithm? The way it does that is, let's say that this is my image, then my image can be broken up into different parts, okay? And those different parts will actually be some features of the image, okay? And then once we have those features, there is a layer that is our complex cells, and this is basically what combines the informations based on those features, okay? Now, in terms of implementation, to get to the features, we make use of a convolutional layer, okay? So to understand a convolutional layer, we have to understand convolution, right? So how many of you know what a convolution is? Raise your hand. Okay, so majority of the class would know what a convolution is because that is very fundamental signal processing trick that we are taught at the very beginning of our geophysics program. So anyway, it doesn't hurt to revisit this. So let's say that I have two functions, f and g, and these are let's say, the time series. So you have one function that looks like this. I have another function that looks like this. So the convolution, which is given by an asterisk, essentially means you take this time series, first of all, you multiply these sample by sample and sum those, okay? Then you shift it by 1 or 2 samples as you desire. Then again you multiply the overlapping samples and then sum those. So the convolution operation is nothing but a shift, multiply, and sum. If your professor did not tell you this, then he simply got you confused. So this is what convolution means, okay? So let's say that I have this time series here, W, and this is time series X, okay? So I multiply this with this, 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 and then I get one number, okay? Let's say this is the number. Then I would shift it by one sample, I would get the next number. No, that is zero. You start with zero shift, and then you apply one sample.
Something is running from 0 to x1 time, and the next is 0 to x2. So what is here? One of the segments. I mean, how to say? We feel it on the other way.
Oh, that is not convolution. That is correlation. Correlation is cross correlation is basically convolution with the negative with the negative shift. Yeah, with the phase shift. Yeah. So that's cross correlation. Okay. So that's your convolution. Okay. But then what do we gain out of this? So let's look at this picture that everybody recognizes in this room because you're all Indians here. So Taj Mahal, right? So Taj Mahal, and then I want to convolve this image with some convolution operator, okay? Now this is a two-dimensional image. So I have to do a 2D convolution. How do I do that? Let's say that I have, this is my input, which is a 3-row, 4 columns, right? And this is my convolutional kernel, which is 2 by 2. So what we would do is we'll take this kernel and I put it on top of this, and then I multiply and add, right? So for the first one, it's going to be AW plus BX plus CY plus EY and FZ, okay? See that? Now, let's say that I shift by one sample, so now my kernel is here, right? So what would be the sum? BW CX FY plus GZ, okay? And then after that, I will put it here, right? And then I get this. So this is a 2D convolution. So once I'm done in one direction, I'll go to the next direction. So that means I will put my template or the kernel here, multiply and sum, and that will give me this. After that, I would put it in here, and that would give me this. Then I would put it on top of this, and that would give me this. Okay? Is this clear? Anybody has any doubt? Okay. So what does it do to my image of Taj Mahal? Okay, so here what has been done is a 3 by 3 kernel where it's 111, 111, 111. That was convolved with the picture of Taj Mahal. And what do you see here? What you see is a blurry image. Okay?
Good question. So that is something that depends on how this is discretized, right? And I don't have the exact number here, but it was more like 100 by 100. Okay? So you have this. Okay? Now, I've changed that convolution filter
to 0, minus 1, 0, minus 1, 5, minus 1, 0, minus 1, 0. So what is the output now? What you see is that the image is sharper. Same 3 by 3 matrix, but with different weights, now gives you a different version of the image. So it's like zooming in and out, right? And you're doing this with convolution operation. Now I apply another 3 by 3 convolution matrix, and now you see that it's able to detect an edge. So tell me, what do you learn from applying a convolution on that image? Different views means different features, right? You can see the edges, you can see the sharpness and all that stuff, right? And the image is built up of all of these components. But here, I put the weights actually to show you this. Initially, you would not know the weights, right? So a neural network that does convolution, these weights are variable. So at the training, it will learn how to find those weight values, okay? So here, in this, yes?
Whenever I have used these type of convolution, like in like low pass filter or high pass filter in image processing, like then we give a little bit padding, but here I don't see any padding. Like, since we used to give on the center point the value.
Yeah, then you can pad it also. I'm going to talk about that. Yeah. So everything that you have done in signal processing applies here. Okay? So if this is a pattern image, and then you have the kernel that is sliding in X and Y direction, and that's your output. Okay, so
in the 1D case, we slide in one-dimensional filter. In the 2D case, we slide a two-dimensional filter. And what about in 3D? Because you can have, so first of all, the question is, what is 3D, right? If you have an image of Taj Mahal that I showed you here, let's see it better, any of these. Is this a 2D or a 3D data?
3D or 2D. Okay, so how is
a particular image file stored on computer? Have you thought about this? You always get all these, all these color maps, color figures. How is that stored? Everything is stored digitally, right? So how is that stored? So typically, what they do is they discretize it, and it's in a grid, right? And in each grid, you have information. If this is a black and white image, this will have an image information in the grayscale, right? Like how dark or how light it is. So they actually use a number between 0 and 255. So we have an image which is 0 to 255. So at each grid, I have a number. That number is either anything between 0 and 255. Okay? And what about the color image? In the color image, what I have is a color is generated with R, G, and B. Who knows what R, G, and B are? Red, green, and blue.
The combination of these will give you the color picture. So for each one of these, I have
numbers going from 0 to 255. So for the color, I have essentially 3 matrices. Okay? One is for the red, one is for the green, another is for the blue. Okay? So this will be 3 layers of 2D data. And we don't want to call it dimension because three dimension is different from 3 layers of matrices. Okay? Because 3 dimension would be what? X, Y, and Z, right? But here we're talking about the 3 layers, and this is called a tensor. Okay? And this software is just called TensorFlow that Google has actually built. Now TensorFlow is the basic package. And the reason it's called TensorFlow is because it's dealing with data, different dimensions, and this is called different tensors, right? Okay. Now there are few terms, there are few parameters of convolution that you have to choose. One is the kernel size, okay? Is it 3 by 3, 4 by 4, 5 by 5, and things like that? What is the stride length? That means how much you want to shift each time, okay? And then there's another thing called padding. So what you do is to pad some zeros around the input feature map so that the output comes out to be the size that you desire, okay? So that you don't have to always change the dimension. Okay, so if you look at this convolution, I have let's say that I have a 7 by 7 input volume, and if I have a 3 by 3 kernel, my output is 5 by 5. Okay. Similarly, here 7 by 7 and the kernel is 3 by 3, so you can have this kind of output. Okay. So I already talked about convolution, and this is the formula that tells you what is the output dimension you can expect. Given the input dimension and given the dimension of the kernel, what is the output? Yes?
What I see after the convolution, the dimensions of the convoluted signal has reduced, or the image has reduced. In this one?
Yeah. So, I mean, it's a smaller dimension, right?
Yeah, but if you convolve 2 times this, then the dimension says one is of n length and another one is for n. Then the final will be n plus n minus 1.
Yeah.
Here it's reduced.
So you look at your problem with the calculation and you get exactly the same thing. Okay? You can add zeros to do that. Okay? So let's say that. So you don't hear what we have done is the very question. Is that, let's say that I have a 3 by 3 matrix, right? And the 3 by 3, then I go to another 3 by 3. Then when I reach this 3 by 3, I don't go beyond this. Okay? If we go beyond this, then that formula will come. So what is definitely done, is you add some zeros and then make it work. Okay?
So, in sense, we don't convolve the last in pixels of the image.
It is not complete overlap. You have a choice. You could. In this picture, we have it. Okay? So typically what is done is you add some zeros to make sure that it's consistent. Okay. So in case of 3D, you have a 3D convolutional kernel, so first you go
direction, then y direction, then in the w direction. Okay? Okay, so these are the tensors. Okay, so now this is the feed-forward neural network that you discussed yesterday, and I also mentioned this morning. So let's say that I have a classification problem. And the classification problem is identification of handwritten digits, okay? So this is a number 2 written on a piece of paper, for example, and then it's just taken a picture of, and then we have it as a picture file, right? So let's assume that it's basically discretized as at 4 by 4 grid. So on each grid we have 0 to 255 as number, right? So now I can make this into a vector of 16 elements, right? So first I put this, then this, then this, and I have a 16 element vector. And this is my first hidden layer, this is my second hidden layer, and so on. So when I am doing a classification problem, I will go through these hidden layers and then, multiply some, then running through activation function, and finally in the output layer, I have 16 values. Okay, so now going from this layer to this layer, what do you see? You see that each one of these neurons basically gets an output by multiplying each one of these input and summing, right? So there'll be 16 multiply and 16 sum. 16 multiply and sum to get to this point, right? Similarly, here. And this is your dense connection. Now, contrast this with convolution. Okay, so this is your 16 element vector, and this is your convolution kernel, which is 2 by 2. So if you convolve it 2 by 2 at any time, you are only doing 4 multiplication and add, right? But then you shift it and you have this again. So for each operation, you are only using part of the data. And it is doing a lot less multiply and add. Okay? So this sparse connectivity reduces the number of parameters in the model. So if this is my convolution operator, I have only 4 weights that I have to worry about, right? Because the weights are shared at the same weight as you slide across. Then you have another convolution block with 2 by 2 that will also have only 4 weights, right? So you have a lot less number of weights in the CNN compared to the dense neural network that I just talked about earlier. Okay? So, I think there was this question. Yeah, so I just told you about the weight sharing. So given that this is a convolutional part of the convolutional neural network, you have this is an input of an image, and we're talking about, let's say, a problem, classification problem. We're given an image. The question that is asked is whether the image is that of a car or a bus or a monument or flower. Okay? So these are your label data. We already have those marked. And the way you help the algorithm to learn or identify these images is first breaking the image into different features. And that feature generation is done by the convolutional neural network. So you have an image of Taj Mahal, and you have said this is Taj Mahal, and then it basically has all of these features here, okay? And that is stored here. So now this is our simple cell, right? There's a simple cell and there's complex cell. So where is the complex cell? So here we have the kernel. This is your convolution filters. You can have multiple filters. And then you have something called a pooling layer. And a pooling layer that is equivalent of complex cell, which basically gathers up information from there and sort of summarizes it. And after all of this is done, we run it through, and then we concatenate. We just turn this into a long vector, then we have a fully connected layer, and then this is the output. Okay? So,
What Pooling is basically one more time. Pooling, you said something. Can you go back, please? So after convolution, you have pooling, right?
Yeah, I'm going to explain to you what pooling is. Yeah.
Now that is exactly what I'm going to explain next. So here we have an image, you have convolution. We also have ReLU because convolution is a linear operator. So you have to go run it through an activation function to make it nonlinear. And then we have the pooling. So essentially what we have is first of all you have convolution, then you have pooling. I'll explain to you what this is, and which basically reduces the spatial size of the feature map. And how it does that, I'll explain in a second. Then there's something called a normalization, and it's running through an activation function. And these are different activation functions that are used, like sigmoid, tan hyperbolic, ReLU, leaky ReLU, softmax. Okay? So what is pooling? Now, CNN pooling is, it's basically, there are two types of pooling, max pooling and average pooling, at least those two. So in max pooling, what we do is, let's say that this is the output of a convolutional block, okay? And now you decide that this 4x4, we want to reduce it to a 2x2. So then what it does, it takes each 2x2 submatrix and takes the maximum. Like here you have 12, 20, 8, 12, and 20 is the maximum. So that is the output in the pooling layer, okay? And here it is 30, 0, 2, 0, so 30 is the pooling layer. And here we have 34, 70, 112, 100, and so this is 112. And then here this is 37, this is 37. So this is your max pooling. Take the max in that box. There is another one, it's called average pooling. So this average pooling actually returns the average of all values. So for example here, I'll take the average of these four numbers, that gives me 13. I'll take the average of these four numbers, that will give me 8, and so on. Okay? So max pooling also sort of performs a noise suppressant. and it actually discards noisy activations. So typically max pooling is used in most cases. Sometimes average pooling is also used, and in some applications you can use both max pooling and average pooling. Okay, and then we have the fully connected network. So this is what you have in the CNN. So in CNN you have convolutional layers, then you have activation function, then you have pooling layer, then you can have another set of convolution layers, activation function, pooling layer, and at the end you have the vector, then you have a dense network, dense layer, density layer, and then you have the output. Okay? And I'll show you some application in the next lecture. But before I do that, I want to show one other architecture which is actually quite useful. Okay? And it's called autoencoders. Okay? So what is an autoencoder? Yes, please.
May you give an example of the geophysical context in which it's easier to understand how this CNN be deployed?
Yeah, I will have that lecture after this. I'll show you some examples. Yes.
So during the pooling operation, we are basically decreasing the size. So we are losing some information there. So if we don't want to lose much information, so what should we use, max pooling or average pooling?
Okay, so max pooling and average pooling does different things. Okay? So max pooling basically shows you
the locations of the feature, and average pooling tells you like the strength of the features. And I will show you an example where it uses both. Okay? And in general, we use only max pooling because all that you want is more of a average average information, and you're collecting it from all of these blocks, right? Okay, so in autoencoders, first I want to talk about how autoencoders actually can be equivalent of something called PCA. Do you guys know what PCA is? Who knows what PCA is? Dimensionality reduction. And then I'll talk about then variational autoencoder. So autoencoders, when they were originally proposed, they're supposed to be unsupervised. And they were used to map high dimensional data to low dimension and learn abstract features in an unsupervised way. So let's say that, so this is general architecture. So what you have, this is your input, this is an encoder, and then what you have here is actually latent variables. And this is the compressed representation of the input data. So after your input to the encoder gives you compressed representation of the input. And then decoder takes this compressed representation and tries to reconstruct your input. Okay? So in this process, what you have is a reduction in the dimension of the data, right? So this is also done using PCA, right? So what is the difference? Well, obviously what you see here is this is a nonlinear operation, and PCA is linear operation. So this is more general than that, okay? So here we have an autoencoder, and here the dimension of the latent space is less than the input dimension. And so if you are able to reconstruct X from H, then it basically means that this H is a loss-free encoding, right? So once you have trained it, then you can apply it on this. And why is this loss-free encoding important? I'm not saying that CNN is used for that, but loss-free encoding is like, when you're watching videos that is transmitted to your TV, it's actually what they send is a compressed version so that it has a very small dimension. But then once it's received, it's decompressed to get to the full picture. So the dimensionality reduction really helps you to keep the majority of the features, or what we say that when you compress and uncompress, then you have little loss, okay? And this is the objective of autoencoders. And I'll show you how you can use it for many other applications. So this is the case where you have the dimension of the latent space that is larger than the input dimension. So in this case, you have to use some kind of regularization, okay? It's an underdetermined problem. So here we still have the ReLU operation, and then again, the training can be done using backpropagation. So now let's look at PCA. So how does PCA work? Okay, so for example, I have the data points that are given by blue line, right? And I represent it, if you represent it in the XY coordinate, then you have to, for each data point, you have to give two values, X coordinate and Y coordinate. Is it possible to keep the same information but using only one dimension, for example? This is the simplest example. And you can say that if you had a line drawn here, you can see all of these are actually very close to this line, right? So I should be able to represent my data using just one dimension simply by doing a coordinate rotation. But then this coordinate rotation, here in the picture, it's very obvious, but in general, you have to do something to learn what is the vector. So the way it works is that you take your input X, and from there you subtract the mean, and then you compute a covariance matrix, X times X transpose. Then you do a singular value decomposition, okay? And then what you do is you look at the eigenvalues, and the eigenvector that is corresponding to highest eigenvalue, okay? Could be 1 or 2. So if it's a 5-dimensional problem, you may reduce it to 2-dimensional depending on how these are distributed, how the eigenvalues are distributed. So in this case, in case of 2 by 2, I have two eigenvalues, U1 and U2, okay? And this U2 corresponds to the vector corresponding to the highest eigenvalue, okay? So now I basically take this and I basically represent the data here. So the goal here is to make sure that when you decompress, you go back to the original data as close as possible, okay? So you can actually show analytically, which I'm not going to give you the math of, that in the autoencoder, if you don't have the activation function, then it's a linear operation, right? If you have a linear encoder and you have a linear decoder, if you have a squared error loss function, and if you normalize your input the way it's done in PCA, this is analytically, you can show that this is equivalent of PCA. But it's more general now because you have the nonlinear operation, okay? So that is the main idea. So here is some application. They've used autoencoders for denoising. So here we still aim to encode the input and not to So, all right, now everybody in this room has done some kind of denoising, right? And one of the most common approaches to denoising is what? You go to Fourier domain and then you filter it, right? Throw away certain frequencies which basically make it look noisy. So what does that mean? Think about it. You have a time series that has 1024 samples, right? And then from 1024 samples, you go to 512 frequencies when you do an FFT. Then you throw away some frequencies. So I have a compressed informational frequency, and then I decompress, and I have decompressed means every frequency, other frequency is set to 0, and then I have noise-free data. So this is how they have used it. Said, okay, I have a noisy output. Let's say that this, you can use this as a supervised neural network, where I put the noisy input of an image, and let's say that I have noisy and noise-free both, okay? And the way I train it is that I input my noisy image to an encoder, then I have a latent space representation. Now, by the way, the encoder and decoder are both CNNs, okay? They have convolutional neural networks. So you take the noisy input, run it through the encoder, you have the latent space representation, then you run it through decoder and you have the denoised output which you compared with your noise-free data. Okay? So in a supervised way, you are able to now remove noise from the data, where you have noisy and noise-free data available. Okay? So here is an example of denoising some of these handwritten digits. You can see what you have here, and beautifully you have generated these images. So it turns out that for random noise removal, it does a pretty good job. Okay? So here is an example of using that in denoising some images that is used in medical studies. So here you have the noisy input. It's an MRI image. This is your encoder, this is your compressed, and this is your decompressed. That's an encoder and decoder. And here is the MRI image with the noise removed. Okay? So understand this? Okay. But bear with me, in the next lecture I'll show you seismic examples. So how do we actually use this in the Bayesian framework? They also have something called variational autoencoder. So in the variational autoencoder, we have the input, and the output of the network is not the compressed variables, but their mean and variances. So it basically models this whole approach using Bayes' theorem. So now we're talking about the probabilities. So what you have is the probability of latent variable z given your input x. You draw a sample from there, you run it through decoder, and then what the output you have is the probability of x given z. Okay? And we can sample from there to get an x hat, and then you can do the training. Now this training is similar, but then the loss function and other thing is computed in such a way that it basically honors the probabilistic information, and that is where the variational idea comes in, and I don't think it's beyond the scope of this course to do that. So when I first learned about autoencoders, what kind of gave me a I got really excited because I saw that, okay, this is my input, this is my encoder, this is my latent vector, this is my decoder, and that's my predicted data. So doesn't that look similar to the inverse problems that we just talked about? We think about this as my data, and the encoder, you can say that this is my inverse operator, and this gives me my model parameters, and could be this is my forward operator that generates the data, and I compare data against data. So remember, you have, say, resistivity, sounding data. You run it through encoder that gives you the resistivity in a model of velocity and depth and conductivity. And then decoder actually does this forward calculation, and I get this. So I have actually used it in a way that is in a way that I just described in some of the inverse problems, and that I'll talk about in the next lecture. So that's all I have on CNN and autoencoders. So I'd like to stop here and open it up for discussion and questions. Okay? Yes, please. Do you have the microphone? Nanya, you can use the microphone, then everybody will be able to listen to you.
So my question is about the latent space. I have two questions on this latent space. What exactly this latent space consists of? And what will be the dimensions of this latent space? And is there any distribution will be associated to this latent space?
Okay, so you have multiple questions, and I have already actually given answers which were hidden during my talk. So I wanted to refresh your memory. First of all, like any other machine learning algorithm, all of these are user's choice, right? So how many parameters you have in latent space is also dependent on how you set up your problem. So when I first learned this, I said, okay, I would give it a linear problem, okay? So I gave that data that I have, remember, the straight line. So what I want is a straight line, right? So I have two coefficients, A and B, or M0 and M1, right? Slope and intercept. So I gave that to this, and what I found is that if I give it like M0 and M1, I get the best fit straight line. If I give M0, M1, and M2, I get the cubic fitting, and so on and so forth. Okay? So this has to be decided in the context of your application. Okay? The second question is there a distribution? Yes, indeed. When you use Bayesian autoencoders, then you get a distribution. You can get a mean value of M0, and you can get a variance of M0, and you can also get the mean value of M1 and a variance of M1. Okay? So it is possible to do that. Okay? Any other question? Are you guys lost? Okay, there's one question in the back first, okay? Can you give the microphone to the other side? To your... No, I think he asked the question first, right? Yes, you can stand up.
And ask the question. When you pass the microphone?
My question is, am I audible?
So my question is, as you were saying, like using this auto encoder, the taking the encoder path to play the inverse operator, and take the decoder and force it to play it as a forward operator. So, like if we are taking the loss from the output and the observed data, uh, like how I can be very sure that the latent space becomes my model parameter? Like,
Well, so what we do actually in the decoder, we're using the physics of the operator. So not using a network for decoder, but we're actually bringing in the partial differential equation to solve it. Okay, so that's one way of doing this. But one fundamental question, which kind of relates to what you just said, is there is a possibility, because I'm just comparing input against predicted input, right? So is there a possibility that I'm actually learning an identity operator? Because all that it does is multiplies with an identity and then does that. Now, to avoid that, we have to do some kind of regularization, and that is done in designing the latent space. Okay. Okay. Who was next? Elisa. Nobody will be able to hear you at the back, so.
So can we do the reverse stuff? I mean, we have clean data and we want to understand the noisy patterns.
Yes, yes. So variance of
Autoencoders can be used for that.
So my question is autoencoders or the PCA component analysis can be used both for both type of data, that is categorical or numerical, or for only one specific type?
No, for categorical variable, I don't know how you can do this. I'll have to think about that. Maybe, yeah, I think you can do that, because in categorical variable also you have different dimensions. Whether it is CNN, I don't know if autoencoder can be used for that. I haven't seen one yet. Yeah, it's a good question.
And for PCA, sir?
PCA, I don't think so, because for categorical variable, again I have to think about it, because you have you can also have for categorical variable you can have let's say that for example it's acoustic impedance and shear impedance, and then you have some structure. So this is your, yeah, it can be done. You have to pose it properly. Whether, so let's say that I have shale, sand, and say gas sand. These are different categorical variable, and they cluster in the different parts. So in the clustering, do we need 2 features, or do we need 3 features or 5 features? So that can be done using, I think autoencoder can also handle that. Yeah, good question. I didn't think about it earlier. Okay.
Sir, I have one more question. Like, because while we are using these machine learning and deep learning models, we normalize the data generally. Like, because different variables may have different ranges. So, in order to avoid that particular aspect, so we normalize. So, the data trains or learns from this normalized data. So, the parameters which were estimated, so like can we think of like how physically they are connected, those parameters, maybe because this data is trained on the normalized values?
Yeah, so that's a good question. These are some practical questions, and you have to scale it back into the original dimension or original unit, and that is pretty easy to do. Yeah.
The parameters estimated can have any physical like after.
Yeah, you can change those. Like you have to use proper units to map those onto the physical variables that you are trying to understand. Yeah. Yeah.
Sir, like, am I audible now? So, just I want to ask, like, I didn't follow what you explained during the categorical data, right? How do we do it without the numbers? Like, either we are converting it back to what was before it before classification, then we're going for PC and then again classifying, or like you can directly do
I
it.
have not implemented it, but what I'm thinking is that here we are basically in the classification problem. When you do the clustering, and there, do we need 2 features, 3 features, 4 features, or 5 features? And that can probably be done with PCI analysis. Yeah, that is done in PCI analysis, and then you can do that. So before you actually define this categorical variable, you can do this PCI analysis based on certain features. Yeah. Okay, so this lecture, I'm going to show you some examples, mostly from the work done by my group with some reference to something related, but mostly from my group. So these are some of the applications. I'll show you first a denoising example and then NMO corrections, which is a very simple problem. Not that you need machine learning for that, but just to show you how it can be used. And then I'll show you how we can actually make use of physics in a ML-driven inversion. Okay, so first example is that of denoising of seismic data by an autoencoder. So I showed you earlier how autoencoder can be used for denoising. इधर क्लास चल रहा है, आप लोग बात मत कीजिए. Be quiet, okay? Okay, so this is a basic application of autoencoder. So here you have a noisy input data, seismic section. You input it to an encoder. You have the compressed representation, comes through decoder, and then you have noise-free seismic data. So here what they have is a set of noisy and noise-free data. So noise-free data is your label data. And then use the same principle that I showed you earlier, just applied to seismic sections, okay? And this seems to be working fine. But then this is the basic architecture, where essentially it's an autoencoder. So what they did here is they use the time series seismic data as an input in a denoising autoencoder. They call it deep denoising autoencoder. So DDAE encodes input seismic data to multiple levels of abstraction, and then it decodes it, like what I explained to you. And what they did is actually trained it with supervised training using synthetic data. And once the training was done, then they can use it on another data set. And these are all basically random noise. So the loss function is again your autoencoder generated noise-free data compared against noise-free data. Okay, and optimization is Adam optimization, which you have learned in the class. Okay, so what you saw yesterday, that Adam optimization was slow, but what happens is when you apply it in machine learning, you're also using mini batches and also using parallel computation using GPUs. So it's really, really fast. So here is one example of synthetic data. This is noise-free data. To that, they have actually added random noise, and this is what the input data looks like. Okay? Seems like a pretty trivial operation. So what they did here, they said, okay, now after I do this denoising, I actually compute a particular sort of like number that tells you how good your denoising is. And I'll explain to you what that is. So here you have 3 panels. And the top, this one is basically some kind of FX decon. FX decon is commonly used in seismic data processing, and some of you have actually used it. So anybody who has actually run FX decon on seismic data in seismic processing? Is there any seismic processor here?
Coherence noise is removed. It's basically to remove the coherence noise.
Yeah, so this is what and what you see is that this is your noisy data, and this is your denoised section, and just one second. And then what they do is they look at the similarity between these two, okay? And that gives you this feature. So what this means is that just one second. Yeah, so this is your data. That's your noise section. And if you correlate these two to come up with a similarity map, this shows you that there is a lot of residual. That means this has not done a very good job. Then this is one other method, some variant of FX decon, and this is your noise section, and that's your similarity map. Okay?
Just add sample by sample.
Yeah. And it's all directional noise.
You can do the convolution as well to add it. You can do the convolution also to add it.
You can, I'm not sure why you would do that, but you could actually minimize the existing color. That's more than the noise, and you can convolve with it.
And this is the denoise section generated by autoencoder. And this is the noise section, and you can see that correlation, or rather similarity map here has very little high values, okay, compared to these two. So this autoencoder actually did deconvolutional autoencoder did a very good job. Okay, so now this is well and good for synthetic data. You could actually use the trained not autoencoder and apply it to the real data, but that does not always work very good. So what they did here is a slightly different approach. So here, what they did is that, okay, for the field seismic data, they'd apply denoise and then generate a noise section, and then generates a similarity map between the noise and the denoise section. And this becomes the objective or loss function that you want to minimize this. So you minimize the similarity between the noise and the real data. Okay? So once they have done that, This is what they got here. So this is a field data, and this is basically denoise section using FX decon, and this is your noise, and this is your similarity plot. This is the decon. Denoising using your autoencoder. This is the noise section, and that's your similarity. And it's very clear that the similarity map tells you that autoencoder actually has done a better job than FX decon. Okay. So we looked at this, and we were also working on similar denoising problem, but it was a slightly different problem. So in the meantime, we came across this paper called Deep Image Prior. Now, deep image prior is actually a very, it's a beautiful concept, and I'm not going to go over the details of the math. So this is by Dmitry Ulanov. So what he did is he posed this problem in a Bayesian framework. Okay. So what he said is that I have denoised and noisy data. Okay. So this is my denoised data, and this is my noisy data. Okay. So the probability, the posterior probability of denoised data given the noisy data is given by the likelihood of the noisy data given the denoised data times the prior probability of denoised data. Okay. He is actually not constructing those PDFs per se. Then what they did was saying that, okay, then I have to basically maximize this posterior probability density. That means I have to maximize this. That means I have to minimize this. And then he says that when it comes to the prior, what if I actually use the random noise section as the prior? Okay. So what they did here is this. This is your noise section. It goes through the neural network and it produces an image, and the target image is the noisy data. Okay. And once you repeat this, I mean, you just do the training, then if you let it go to full convergence, it will actually reproduce your noisy data, right? Now pay attention to this. Your input is random noise, and your target is the noisy data, and there is a convolutional neural network in between. And if you run the training, then if you let it go all the way to minimum error, it will actually produce an image of the noisy section. But what they showed is that if you stop early, then it actually goes through denoise data before it goes to adding noise. Okay? So that was quite intriguing. However, the problem is where to stop, right? How do you know this early stopping? And this process is very, very fast, so you can actually have this coming in on your screen, and then you can decide where to stop. But it's kind of tedious. And of course, it was quite successful in removing random noise. So with my student, Dmitry Voitan, we were looking at a slightly different problem of denoising. What we were working on is how to remove noise from migrated seismic images. Okay? Now, if you have inadequate shots, the migrated image will have different kinds of noise, the coherent noise. These are all coming from artifacts, migration artifacts, right? We have migration smiles and all that stuff. So can we remove that? Now it turned out that if we actually used our simple deep image prior, it removes the random noise, but it cannot remove the coherent noise of autoencoder. So what we did was we turned it around. What Dimitri did is to turn the problem around. This was also my idea. But he said that we use the same deep image prior, but we say that my output is velocity. Okay. For migration, we have a velocity. So we take the difference between these two and call this a perturbation in velocity. And now I have the impedance, so I can generate my synthetic data. And then I compare it against my RTM image. And then I optimize the weights of the neural network. So what have we done here? What we've done here is we have added the physics. Okay? Because when you generate synthetic data from the model, it's a normal incidence synthetics. It does not have the migration artifacts, right? But the RTM image has the migration artifacts and also the coherent noise. So the optimal training will basically give you the noise section. And that actually worked beautifully. I can show you here in these pictures. So here we have the noisy image. This is your standard deep image prior. This is your our approach, and this is a synthetic model, so I knew the true reflectivity. So what you see here is this is the noisy image. It has a bunch of artifacts, and if you look at the zoomed version of the boxes, you can see that this is my noise. It's still in here, but we have been able to get rid of that. Similarly, in this one, you can see that deep image prior actually removes a lot of the coherent noise. But if you look at the zoom section here again, you can see that we have a much cleaner image from the physics-based deep image prior. So this one shows you noisy image. This one is de-noised, and this is the removed noise. The reason we wanted to plot is that it's not perfect. It still has, some residual, but overall it does a much better job compared to, for example, if you look at this, these are all artifacts, and that's all gone. Okay, it's not gone completely, but it's still, we have something that is much better looking than what you had in the original one. Okay, so this is one example. Then the second example was that of normal move-out correction. This is something that everybody is aware of in this room. So in normal move-out, what is typically done is we estimate a velocity, which we call RMS velocity, which RMS it represents sort of like equivalent velocity when you replace a layered medium with just one homogeneous medium and its equivalent velocity. So if you have two layers, you have medium 1 and medium 2 with two different velocities, V1 and V2, RMS velocity of this layer would be given by an effective velocity, which basically assumes that this is homogeneous. Okay. Now this is a very simple approach. It works just for quick and dirty velocity analysis, but you can't really use it to convert to depth. Okay. So there was this work by my student Ritam Biswas. He used a supervised learning approach. Now, in the supervised learning approach to NO analysis, we used CMP gathers and picked NMO velocities. So there was a seismic section for which we manually picked velocities, and now we wanted to train a network to learn the mapping from a CMP gather to velocity and then see how it looks like. So in the training, he used this this kind of data. So remember that to pick a velocity, since your travel time window basically sees more than one reflector, so rather than using point by point velocity as an input, we actually used it as a sliding window. So this, what he used is a recurrent neural network. Okay. And the architecture of the recurrent neural network is given here. I'm not going to go into details of that. So here is an example. So this is your brute stack, and this is your training, and you can see that in about 10, 20 iterations, we're able to train the network. So here is our result. This is really your manually picked NMO velocity, and this is your predicted NMO velocity. So for training, what we did is this has about 1,000 CMPs. We only used 80 CMPs for training, and then we applied it to the entire line. Okay, so the quality of stack is about the same, but then the velocities, and you can see that some of the velocities, it's on an it looks pretty much similar to what we got from sort of manually picking the velocities, but there are some differences, and that is because that is the level of details that cannot be resolved by NMO velocities. Okay. So this the main advantage of doing this is that if you did the NMO analysis at a few points, train the network, and then in one step you can get the NMO velocities everywhere else. Okay. The next thing we did, this is like a class assignment. I teach a course on machine learning for geosciences. It's a one semester course. In fact, I will be teaching that again starting in August in our fall semester. So while thinking about some problems, we just one time I told my TA that let's try to just give a homework exercise for using clustering for NMO velocity picking. So this is really not a big deal, just for as a demonstration. So what we did here is that, okay, now this is my CMP gather, and this is our resemblance plot, right? Everybody pretty much knows what resemblance plot is. Here, this axis is velocity, and this is the two-way time, and this contour shows you the quality of NMO, right? This is the semblance value. So typically, what these are generated, and then manually we pick the center, and sometimes we can look at on the screen how flattened those gathers are. So the task was to basically, we gave the CMP gather to the students as, okay, you generate your resemblance panel and let a clustering algorithm pick those center of the cluster. Okay. So this is what they did. This is kind of clustering they got, and this is your NMO correction. So this is with the manually driven, manually picked velocities, and this is with the clustering. So what you see is that they don't look a lot different except for very large offsets. And there you have the NMO stretch, so that could be that is probably the reason why you're seeing those differences. But clustering also. This is not something publishable, but just to get the students their hands dirty so they know how it works, and then go from there to more difficult problems. Okay. I want to show you one example. This is the work done by my former student, one of my first batch students. This paper was published in 1998 when people just hated you if you worked on neural networks, okay? But we went ahead and did that anyways, and so this is one problem that I actually picked very carefully. And here we are doing velocity analysis in tau p domain. And in tau p domain, what happens is you first take the gather and transform it to tau p gathers. So here the reflection hyperboles, they get converted to ellipses. And this is basically sum of the ellipses. So now you can match the tau p trajectories. Okay, so this axis is your p and this axis is tau. Now, if you can match these trajectories, you get a velocity model which is interval velocity, which is the actual velocity that you can use to convert to depth. And RMS velocities are really not that useful. They're not at all useful to converting to depth. You can use Dix's equation, but Dix's equation does not work everywhere. And in certain circumstances, they do work. But so here, if you want to use tau p analysis, you have to sit on a monitor and pick these events and then fit these paths using your equations for move out, which is tau p is equal to tau at 0 times 1 minus p squared by v squared. And this v is your interval velocity. Okay, so then what we thought we could do is we can use a neural network for doing this. Okay, so what Carlos did is this, is that we put in a CMP gathered in tau p domain into a neural network, and the output of the neural network is velocity. Then I calculate the tau p NMO using the physics equation that I showed you earlier. I flatten the gather, I calculate an error function that measures the flatness. And then, rather than updating the velocities, we were updating the weights of neural network. So this is one of the first, I think it is the first application of,
Data.
This is your gathers.
Observed data.
Yeah, observed data. Yeah.
Velocity was the simulated. Velocity is the output of the neural network. So your input is the CMP gather. Okay. We will get observed data, but how we get the velocity? Because we have a trained data, we need velocity data. Yeah, so we will put it in the neural network and say that this is my velocity, right? But how do I know that this is the right velocity? Right? So then I compute my tau p,
the velocity dependent move out in this equation. Okay? Once I get that, then that I can use to flatten the gather. And if it's not flat, then we know that the velocity is not correct. When it gets flat, then this is the right velocity. So that then used to update the weights of the neural network. Now those days, none of these optimization algorithms were available. So, and here we didn't know how to actually use backpropagation for this problem. So we used simulated annealing because it was a few parameters and we trained it with simulated annealing. And this is the data set. This is the field data. This is from the east coast of the United States, from Carolina Trough. And in this line, we chose three different parts of the line, a few CMPs, and we trained the network using data from those three zones of CMPs. So here we have the flattened gathers that we obtained from three different zones, and then we applied it to the entire line. Okay? And once we do that, then we get a section that looks like this. Of 1D seismic inversion, okay? Post and pre-stack inversion. Physics-based inversion is what I talked about yesterday. It was the day before. We actually discussed that. And here I'll show you how neural network is used, okay? So this is the first one I'm going to show you is a supervised approach using CNN. This is the work done by Stanford group, and Vishal Das, who's a student in this department, actually did the work. So here, what they did is actually quite simple. Well, the architecture is not simple, but the idea is simple in the sense that you have an input seismic trace. Let's say this post-stack seismic trace, and you have known impedance. Okay. So what you do is you design a network so that it learns the mapping from seismogram to impedance. Okay. So it's just the training process. So essentially this is doing the inversion for you. Okay. But then when you're using a supervised approach, you have to be careful about how you generate your training data, right? So what they did is actually being a very strong rock physics program there, they generated data from different kinds of rock physics model following certain geostatistical simulation and trained the whole network with the data set that they had generated. And there is an example of inversion. This is the trace match, and this is the inversion for P impedance. And the red one is our standard deterministic inversion, which is actually quite good. Of course, this actually does not pick up all the details which you expect because it's doing it pretty much in the seismic band. But the neural network actually pretty much mimics the well log. This is good, but this could be, unrealistic because with seismic trace, can you actually get all those details? But those details were present in the training data, so it found those. So they then applied it to some data from Node C. This is the three-dimensional volume, and here is one example of a seismic trace. And this is where they're comparing the log of acoustic impedance against what is derived by neural network, which is in red. And this is the interpretation in the entire volume. So what we did is slightly different. We said that since we don't have training data, we only have a few wells. Here they trained it with synthetic data. So what we did is use the same idea that I used in our NMO correction. Yes. Rock physics model to just generate synthetic models and synthetic data. Synthetic logs. Yeah. P wave velocity,
and then they generated synthetic traces.
Okay, so here is the Stanford guys' approach where they said, okay, I have my input trace, I have the convolutional block, and then I have the output, which is my impedances, and then or velocity, P wave velocity, shear wave velocity, and density. I compare it with the known result, and I basically backpropagate, right? So what Rhythm did is this, saying that, okay, I have the input seismic traces, I run it through the network, I have the P wave velocity, shear wave velocity, and density, or P impedance, shear impedance, and density. Then I run the forward operation. Okay? So this is your encoder, and this is your decoder. The physics is the decoder. Okay? And then I generate synthetic data. So here there is no label data. There is no training data. We're comparing trace against trace. Okay? And the quality of the inversion result from this is dictated by the quality of the match between the input trace and the predicted trace. Okay? So here is what we have against the log, and this log was filtered to this frequency band, and we saw a pretty good fit, and this shows you the training. So what is the advantage of doing this? The advantage of doing this is that, well, first of all, if you look at our workflow, it may seem to you that we are essentially doing seismic inversion, but using neural network, right? So what is the advantage of doing this? The advantage is that I can train my network with a certain percentage of the CMPs, and then I can use the trained network to invert every other CMP in one iteration. So it's going to be pretty fast. So here is the comparison. So this is the prediction using neural network, and this is using, say, Hampson-Russell package. So you can see that more or less they're matching quite good. Okay? And the same thing I have for VPVS, and this is your VS section, and you can see that this is kind of matching all right. So there's one other well, and where we are showing you is the fit, and this is the low frequency model, and you see that this is actually working quite good. Yes?
Which is from deep learning, you are getting one output for the impedance, and from that output you are getting seismic. Are you using two loss functions for optimizing this network? Like one for the output, impedance output, and one for the seismic sensors?
Well, so you're asking whether I'm using two.
Loss functions.
No, I'm using only one loss function, which is the difference between observed data and synthetic data.
Not for the impedance output.
We don't know the impedance, right? So we can put some constraints on the impedance, but we are not matching impedance by impedance, like everything by the group, by the standard group, okay? So this is working pretty much like inversion,
Except that the inversion is being done by the neural network. Okay? Any other question on this? So there's one other thing we did here, which is kind of interesting, by one student, and she's an electrical engineering student. She worked with me from India, and she worked with me online, and we got a paper in IEEE on that. Here we use something called attention module. And attention plays an important role in human perception. And one important property of a human visual system is that one does not need to attempt to process the whole scene at once, right? You can choose certain areas where you can pay attention to. And this can be implemented using something called CBAM. It's a convolutional block attention module. So this basically has two parts. It uses both max pooling and average pooling, okay? And this process actually finds the channel attention and spatial attention. That means it has, out of all the channels, it tells you which one is more important than the other, okay? And I'm not gonna go into details of the theory, but this is what it looks like. You have the input, you have the channel attention module, and then you have the spatial attention module and this. So we haven't given an input image. So you have two attention modules, channel and spatial, and based on that, we compute our output. So let's look at this model. This is a true impedance. It's actually quite interesting work. And here, I'm showing you some of the convolutional networks panel output. Okay, so this is the one. We have the features, which is input to the attention module. Okay, So here you can sort of see the structures, but not very clearly, right? And when you actually run it through the attention module, now you can see some of those boundaries coming out very, very pronounced compared to what we had before. So this is one, and this is this. This is another set of input features, and that's your CBAM output. Okay. So now, if you look at the results, this is your without CBAM, and this is with CBAM. Now, this is not a fair comparison in the sense that I stopped it at a lot less number of iterations here because this converges much quicker. And to compare the two, I chose the same number of iterations. And you can see that with a lot fewer iteration, your attention CBAM based inversion actually gives a much better fit to the log compared to the one without the CBAM. Okay?
Okay, so this one basically is normalized.
So this is basically time, and this is impedance, and this is normalized. So this is the sample number. Yeah, good question, because we have corrected that in the paper now. Okay, like I said, this was done by an electrical engineering student doing PhD, and so she looked at this only as signal, and then she said we wanted to apply it to seismic signals. Okay, so now let's look at a slightly different approach. It's called cross-shaped Boltzmann machine for petrophysical inversion. Okay, I hope I'm not bombarding you with a lot of terms, but try to focus on the input, output, and the result. Okay, and maybe at some point you'll be able to learn some of the other some of the details. So this was done by one student of mine, Son Fan, and Son actually came from industry, so he understands. Yes.
What is petrophysical inversion? What do you try to do?
Yeah, so there we try to predict
Like porosity, saturation. I have an example. I'll show you that. So here, so yeah, this is for petrophysical inversion. So we want to get porosity and saturation. So here we use something called cross-shaped Boltzmann machine. So I'm going to skip those details. So what is done here is we have, let's say we have porosity V shell and water saturation at the well location, right? And we have the angle gather at the well location. So this machine or this neural network actually trains the data with all four. And once it's trained, you can go from one to the other, okay? And here is your seismic section, one of the seismic sections to which we applied. And this was the paper that was published in AAPG Bulletin. So this is your, what they call hot shell. And this is a log. And we had 1, 2, 3, 4, 5, 6, 7 wells, of which we used, these are not necessarily on this line. And this is actually a crooked line, but it's shown as a 2D line. So here we have used this to train a network, and this shows you inverted porosity at the 7 location. This is V shell, and this is SW. Okay, so of which we use 5 wells for training and 2 for validation. And once you have done that, then we apply it to the seismic section, and then we got this porosity and V shell. Okay. Now, there was a recent paper by Divakar. He took our physics-based seismic inversion approach, and to that he added rock physics, okay, to be able to directly determine the rock physics parameters. So his approach was this. He said, okay, I have an input trace. For example, if this is my post-hoc trace, I run through convolutional layers like what he did before. And then I have the output is now porosity. Then he uses a rock physics model that maps this to VP, VS, and density. Then he generates synthetic traces, compares it against the observed traces. Okay. Other thing he did is also, since that was not giving robust result, he also used the porosity log as input. Okay. And then in his loss function, he has seismic minus seismic and log minus log. There was one question that was asked before. You asked that. Here they did both. Okay. So here is an example of how well they do. This is your training set and test set, and you can actually see how well they're predicting the porosity. So now you can actually run this to estimate all of. Either you can use that cross-shape Boltzmann machine, or this approach to actually directly get to the rock physical parameters. Okay. Any question? Now I'll go to the full waveform inversion. Okay. Again, we don't have a real data example yet because this is still some work in progress. So this can also be either supervised machine learning or unsupervised machine learning, right? So there is a paper that talks about supervised machine learning, and they call it inversion net. This is the paper from Los Alamos National Lab. And their approach is that we have a bunch of shot gathers. I run it through this network, and my target is the velocity model. So they train the network with a volume of seismic data and subsurface model, velocity model. Okay. So here, and this data set actually is available open source. You can go to this, you can search OpenFWI, and you can download the models and the data if you like. So what they did here is they generated some structure here, and some of these are basically small models. They have 36,000 models, 100 by 100 grid points. There's something like curved layers. They have also the folded layers and things like that. So different kinds of models, they trained it, and this is the data that you have. These are different shot gathers, and they trained their whole network with this data set. And this is what looks like. This is your training loss, the blue one, and this is your test loss. So the test loss, it goes up and down, and then finally goes to here. So how does the result look like? This is what the result looks like. Here we have, this is your true model in the your leftmost panel. And this is the supervised neural network output. And this is another supervised neural network with slightly different architecture. And these are using FWI. Okay? So their claim is that that neural network actually does a better job. But you have to take this with a grain of salt, because the reason they're getting all those details is because this was already present in the training data. If you did the inversion using seismic data alone, you will not see all the details, because seismic data is not seeing all the parts of the model. Okay, so in other words, through this process, they are actually adding some kind of prior. Okay. So our approach to the same problem was slightly different. So I explained to you as to what full waveform inversion is in yesterday's talk. Was it yesterday? Yeah. So you have, I don't know if everybody attended, but you have a true subsurface model, which we don't know. You have this observed data. So we assume some model generates synthetic data, take the difference, calculate the loss function or the objective function. Then we use gradient descent, which you all know what it is. And then you update your model and this go in here. And yesterday I showed you the big problem with this is the local minimum issue. If your starting model is good, you get a very good solution. If it's bad, then you get a solution that is very different from the actual model. And this happens because of cycle skipping. It's a local minimum problem. You get stuck in one of these minima rather than finding the global minimum. So typically we go through multi-scale FWI. That means we go over frequencies. So you start, say, example, 0 to 3 hertz, 3 to 6 hertz, 6 to 9 hertz, 9, 12, 9, 12, 15, and 15, 18. And then once you put this together, this is your true model. That's your starting model. This is your inverted model. But you had to do like, and also there is some information already in the starting model. So what we did here is we used, again, an autoencoder type of architecture where we put in the short gathers and the output is the velocity model. And then we solve our forward problem. So this is how the network looks like. You have short gathers. This is your autoencoder. This is your velocity model. Now I can solve my PDE, and then I generate synthetic data comparing against observation, and then I backpropagate. So this approach is the same as what we did in NMO, the same as what we did in pre-stack seismic inversion. We're using this, just that it's computationally more expensive. So we did that, and we tried to this model, which is a SALT model. It's pretty well known. This is sort of like a test model given to people working in imaging or FWI. And what we got, this is a true model, and what we got for inversion is this. It's actually pretty close. Now there is a difference here. There is no starting model here. Starting model is flat. Okay. So why is the starting model? So let me show you how the results look. So at different iterations, you can see in the starting model, iteration 10, you have very small perturbations in the velocity. So it's only matching like the initial part of the data. And then slowly, as the iteration progresses, it builds the details of the velocity model. And by the time you are in iteration 2000 or 3000, it has actually captured this entire model. So this is something that we learned. And it turns out that this staging over frequency that I showed you earlier is being learned by this network by itself without being told that you stage over frequency. Okay? And I'll show you a little bit of mathematics as to why it's working that way. So before that, I show you the results with noisy data and so on. So there's something called spectral bias of NN. So what it says is that neural networks, especially CNN type of networks, they're biased towards lower frequencies. Okay? So it actually picks up the low frequencies and then it goes to next batch, then the next batch, and so on, which we saw here. So if you have input as X, then the first layer we will have, this is your linear sum, and this is your activation function, right? So at the end, we have L, which basically has this, right? Now, if you think of, for simplicity, let's say that my activation function is a tan hyperbolic function, okay? If my activation function is a tan hyperbolic function and only one hidden layer, then I have this as the output, right? So if I go now and I write down the Fourier transform of the output, this looks like this. Okay? So now I look at the output, which is HK minus our original data or the predicted data. And here I'm taking a derivative with respect to the model parameters. What you see is that we have this exponential term, and this K is your frequency. So what you see is that this actually biases you to go from lower frequency to higher and higher frequencies, okay? And that is exactly what we observed without actually telling the network to basically do a staging over frequency. And this actually was one of the major breakthroughs in our learning of deep networks. And now we're working on a whole bunch of applications on real data and so on. So that's pretty much it as far as this talk is concerned, this lecture is concerned. So we'll take some questions for a few minutes before Soman starts. Yes, can somebody pass on the microphone?
Sir, in one of the application, deep image prior, you said that when you start with the noise model, ultimately we get the noise structure of the section. So in that, so does it capture all the noise?
It does not capture the coherent noise. It can only capture random noise. That's what I showed you, right?
So like we work in the continuous monitoring. So we have the knowledge of the noise, complete noise. So by giving that knowledge, can we capture the complete noise?
Absolutely. You can combine it with deep image prior to do that.
Okay.
Absolutely, yeah.
Okay.
Can you go back to the slide where we were showing the salt body? Yeah.
This one?
No, previous one. Yeah. So here you have said that we can use this physics to generate the synthetic data and then backward the loss. Can you tell me like how the loss is getting backward from the simulator to the neural network and how it is
Yeah,
updating?
so you have to, so we are calculating the two ways you can calculate the loss. One is using a joint state method. I mean, the gradient, you can the loss is the L2 norm or L1 norm. So there are two ways you can calculate the gradient. One is what we use here is an adjoint state method. And you can also do this automatic differentiation. I mean, yeah, you can do the auto differentiation, AD, okay? And that also works equally well.
Like this, when we are calculating the solving the PD, we are not doing it. We are not doing it with the computational graph. Like we have to do it in some another.
Right, but you can always update all the parameters that basically led to the coefficients of the PD.
Okay.
Okay, because PD is coefficients of the velocities in this case, right?
Okay. I have another question also. Like in the autoencoder,
Yeah.
like, most of the if I take it as a matrix or a as an image, the entire shot gather, the most of the pixels contribute to the background noise. Then input data which has more number of noise and less number of useful information, how it is learning the how it is denoising the.
No, I think first of all, random noise does not cause as much problem in FWI because the loss function is able to eliminate that. But the point you have is that we have a lot of noise, which is not entirely true, especially in marine data. You don't have that much noise in the beginning, but even if you do, we could apply some kind of pre-processing to remove that. And also, you can be clever about about generating the data by sort of muting some part of it, and then, and I mean, if you take the data, you can mute some part of it which you think is noisy, and then you can pass it in there.
Actually, I'm asking this question because I'm having a tough time using a autoencoder for a patch of different seismic sections. Like every time I use it, it learns the background. It learns the small amplitude variations. It's never learning the traces.
So you could actually put some weights in there also. If some of the data set you can apply, if you think they are not as useful, you can apply small weight to that.
Okay, thank you.